Good morning. A warm welcome to the Humanist community in Silicon Valley Sunday Forum, to those joining us on Zoom and to those joining us on Facebook and in person here at the Community Center in Mountain View. My name is Ray Sunby, president of the Humanist community. The Humanist community is a chapter of the American Humanist Association. Humanism is a secular and reality-based philosophy of life that affirms our ability and responsibility to lead ethical lives of personal fulfillment that aspire to the greater good. We value freedom, health, happiness, fairness, compassion, and using science and reason to acquire and apply knowledge. If these words describe your thinking, we invite you to become a member of the Humanist community if you've not yet done so. Membership forms are available on our website at humanists.org. A special welcome to those who are with us for the first time. We invite you to continue listening to our weekly forums and other events. You can find all our events listed on the website, humanists.org. Please aid us in continuing to present these forums by donating to the Humanist community. You can find out how to donate to our organization on our website, www.humanists.org.
Thanks, Ray. My name is Alex Savasi. I'm vice president of the Humanist community. Today, Christine Hoffman will discuss a higher power critical to the creation and sustenance of human life on Earth, the sun. The main focus of the talk will be on how energy can be harnessed to electricity, heat, and cool our homes. We'll cover the basic photovoltaic and concentrating solar thermal technologies. Finally, we'll touch on the limitations and challenges of this amazing power. Christine has been a lifelong environmentalist and waste reduction advocate. She holds a PhD in applied mathematics with a thesis work focusing on optimizing non-imaging solar concentrations. I have to ask you what that means.
Well, you'll find out in just a few minutes.
Okay, she currently teaches machine learning and data mining, but also aspires to become an entrepreneur for a company that uses technology to solve logistic issues of container reuse. So please welcome Christine Hoffman.
Thank you. Okay. So a great introduction. Oh, I realize I got to share with my Zoom folks over here. One sec. But yeah, I'm Christine. So thank you for the introduction, and Alex. And I have a little presentation, so I'll share my screen so everyone on Zoom can see it as well. Okay. So as mentioned, I'm going to give a talk on the power from above. So I thought I'd make a little joke since it's Sunday. I'm going to talk about a power that is, it's an incredible higher power. It's critical for all creation and vital for the sustenance of humans and life on Earth. And I think that it's already sort of given some hints at what I'm going to be talking about. But what kind of power do you think this is?
Magic.
Magic, yes. It's the sun. So yeah, the sun's higher power, it's above us, right? So yeah, no sermon on anything else. So I'll first talk about how the sun creates energy. So this is just one slide, so inside of the sun, there's a nuclear fission that occurs. So you have hydrogen atoms, which on the periodic table, they're the lightest elements. And they violently collide with one another in the sun's core, and they fuse together to create helium. And which is, the second element on the periodic table. So I think this is really cool because this is sort of how you get heavier elements. So when I first learned about this and like solar and things like that, I didn't actually know how you get, bigger elements like carbon and nitrogen, all those other ones down the periodic table. They collide together in sort of a fission, and it takes a lot of energy to get them to react. When they do, they also release a lot of energy. So this nuclear fission is a proton-proton chain reaction, and it releases energy in the form of waves and particles. So that's like those, you'll see those sunspots. When I had an internship at NASA, there's a lot of people researching the sun, and they're really passionate about it. And I don't know very much about this sort of stuff, but if you talk to them, they're really excited about it. And they'll tell you all about the sunstorms and things like that. So this energy that comes from the sun in waves, it warms the earth, as you probably know when you go out on a hot summer day, not like today, on a rainy today. And it causes wind and weather, and it sustains all plant and animal life on Earth. So yeah, the sun is absolutely vital for us. So how can we harness this energy to use it to, say, electrify or to heat our homes? So there are sort of two, let's see, can I realize you can see this too. Let me just move it out of the way there. Okay, so there are two types of solar energy that we can use to harness this energy in two different forms. So there's photovoltaics, which I'll talk about first. And those are the photovoltaics denoted as PV. You probably heard it as short formed as PV. They convert solar energy directly into electricity, into electric current. And they're made out of semiconducting materials, most of the time silicon, but you can get other materials as well. And they produce electricity during daylight hours, obviously when the sun is shining directly on them. That's when they produce electricity, but they don't after the sun goes down. And the second type, which I'll talk about second, are solar thermal concentrators. So instead of transforming the sun directly into electricity, they concentrate the sun's energy onto some a tube. It's filled usually with some kind of fluid, and the light is concentrated and collected in the form of heat. So it's going to heat up this element, and the collected solar energy can be more easily stored as heat rather than electricity. As you know, if you've ever want to put solar on your house, if you want to have sort of electricity after the sun goes down in photovoltaics, you have to install a battery, right? And that's one advantage of solar thermal, is that it, as long as you heat this up, you can store it a little bit more easily after dark in insulated vessels. You can store the heat. So let's first talk about photovoltaics. All right. So that was the rooftop solar that you see. Oh, and I already mentioned, I was going to ask you guys, the audience, what solar cells are made out of. Do you guys know what's made out of silicon? Is silicon solar cells probably? Okay. You guys know a little bit about solar, probably basic stuff. So, so silicon, so I'll talk about how this electricity is made. So it's made out of semiconducting materials, which are right here on, silicon's right here on the periodic table. Okay. And you'll notice that it's sort of it has 4 valence electrons. Okay. So this would be a mini chemistry lecture. Okay. So those 4 valence electrons, do you guys know how they like bond to one another? So if you have 4 valence electrons, it sort of bonds in a tetrahedral shape and makes a lattice structure. Okay. So you'll have, these are the silicon, for example, semiconducting cores. Okay. And they each have these 4 valence electrons, and they share, you need 2 valence electrons to make sort of a bond, like a pair. So it'll bond, each of these 4 will bond with one other one from a neighboring silicon atom and make a tetrahedral lattice structure. I could have put a picture of that too, I guess, but this is sort of the 2D version of the tetrahedral structure. It just shows that each 4 is sort of bonding to the next one. Okay, and so these are covalent bonds. So what they wanted, what they do to sort of, get some properties that we want, which we'll talk about in just a little bit, is that they dope silicon, Okay, you probably maybe heard of silicon doping. And so what they do is when they grow these silicon crystals, these tetrahedral crystals, they'll put minute quantities of some other atom in the crystalline structure. So those are generally elements from the third and fifth column of the periodic table. So things that have only 3 or 5 valence electrons. Remember, silicon has 4 valence electrons. So in this case over here, if you have phosphorus, okay, has 5 valence electrons instead of 4, if you just put one sort of impurity, let's say you just put one phosphorus atom among a whole bunch of like 10,000 silicon atoms, that silicon is going to want to form that tetrahedral structure, right? But it'll say, okay, we'll accept one impurity over here, this phosphorus atom. It has one extra electron, but we're still going to bind it sort of in a tetrahedral structure that we want. And you get this extra electron just sort of hanging around, and it can sort of be stabilized by the neighboring silicon positive cores, but you get sort of an excess of negative in your crystalline doped phosphorus. And then they take another layer and they are growing the silicon and they're this crystalline form, and they take for example, boron, and boron has only 3 valence electrons. So over here, you'll see that this silicon, right, it wants to make a pair to make that covalent bond. But this boron, it doesn't have 4 valence electrons, only has 3. So it shared its 3 electrons over here. And this one over here doesn't have sort of any neighbors. So you get sort of an excess of positive charge in the boron doping layer. So does that make sense? Let me know if I'm not explaining this clearly. So you have they grow this, and you have an interface of 2 uniquely doped layers, and they join at an interface. So you have the N-type layer, and that's generally made with the column 5 elements like phosphorus, arsenide, okay, that you dope. You're doping minute quantities of these elements in your silicon crystalline lattice, and you're gonna get an excess of negative charge. Remember those you get those extra negative electrons. They're sort of hanging around, and they're stuck. They're trapped in this silicon tetrahedral lattice, but they don't quite want to bond in that way. But it's sort of, they're forced to do it because there's only a tiny bit of them in the crystalline lattice. And then in this layer down here, this is the P-type layer. You can think of positive and negative, right? This layer here has the positive charge. And those are made with the column 3 elements. That's the aluminum, gallium, and indium, okay. And this layer here has that extra, you can think of it as like an extra proton, right? It's that boron or whatever that can't bond. It doesn't have the extra electron to bond. So you get sort of an overall, you get like an excess of positive charge, you could say. So at this interface right here, this is often called the space charge region, okay? You'll have they have like extra negative charge here, and you have sort of extra positive charge here. So at this, you'll get some electrons that diffuse sort of from this layer up here of silicon. They'll diffuse across this boundary towards the positive charged layer down here. And this creates an electric field, okay? And so the electric field is going in this direction, all right? And then what happens is, so the sun shines down, and they try to make this N layer, this this excess electron layer, they try to make that as thin as possible, okay? Because ideally you want the sun's energy to come down. And you've probably learned in chemistry that, you know, when an electron gets excited, it moves up, right? And so in the the shells, right? You have these valence shells of electrons. So again, the excess electrons holes diffuse to opposite sides of the junction, and these exposed ionic cores, they create this electric field or drift current. Okay, and then the sun shines down, and ideally it goes through the this N layer, and it excites electrons in the P layer, in this positive layer. You're exciting the electrons of the silicon, and they get excited and they jump up to the higher valence shells, and they because of this electric field, they'll go across to this top side here. Okay. And then that's what creates this push of current. Now you got current flowing, right? So you can hook a light bulb up to this. You got the sun exciting the electrons and pushing them up here, and then you get too many electrons. So they would like to get back to here. So you can flow those through a wire, and you got some electricity. Now you have current. Can light up your house, light up the light bulb. All right. Any questions on that? I hopefully did a okay job. Explaining that. So if you're thinking about going solar and you think it's really cool, wow, you got like, free electricity from the sun. You can heat up more than a light bulb, your house, your AC in the summer. Now's the time to go solar. So this is just a plug really quick for everyone that lives in California. Yeah, someone wants to get in. I'll just say yeah. Net metering is ending, so I'll talk briefly about net metering. It's not for sure ending, but it's probably ending. I should say that. They're going to vote on it in I think 5 days, like on around December 15th, they said. So net metering is a great deal, okay? And we'll talk about that in the next few slides and why you should try to get on net metering. So if you don't have these solar panels on your roof, you should get them fast, like very soon. You got like 120 days. So call someone up, get the permits, get them on your roof. That's what I'm doing right now. I just bought a house. So I'm super excited to get some solar on my roof. Hopefully I get it in before the cutoff date. So, whoops. So what is net metering? So net metering is sort of a policy that was put in place for how you sell and get electricity from the grid. So most likely if you put solar on your roof, right, like I said, the sun is shining down, it excites those electrons and it gets the electrons moving, and you get electricity during the day. But as soon as the sun sets, right, you're not going to get any power. So at night, I'm most likely you're still going to have to be connected to the grid, which is probably PG&E if you're like me, which is really expensive. And PG&E will send electricity through the power lines, and you can use it to still turn on your lights and power your home. And as you probably know with your electric meter box outside, whenever you turn on a light or run the dishwasher or the washing machine, your meter moves forward. Okay, you can think of it as a clock. I just had a clock. I just put a clock on there as like an example. It moves, it runs forward, and it clocks up how much electricity you're using. Okay. But then during the day, when the sun comes up, net metering has it that your clock runs backwards. So when your sun is shining on your panels, and let's say you're producing a lot of electricity, more than you're using, you only have a few lights on in your home, and the rest of that electricity just goes back on the grid into the power lines, goes to your neighbor's house, down the street. Your meter will run backwards. So you will get credited sort of 1-to-1 for any electricity that you used at nighttime. You can get it back sort of by giving energy during the day, a little bit more during the day that you don't use. So this is a really great deal. And you should get sort of, if you can get grandfathered into this great plan, you should try to do it and get solar in your house right now, like right now, in the next 3 months, should be on and running. And the reason they're changing this, one of the reasons, so of course, I think PG&E complains a lot. They get a ton of money. I lived in Santa Clara before this. Anyone live in Santa Clara? And in the city of Santa Clara? No, Santa Clara County. Santa Clara County. Okay, so you have to live in Santa Clara City Santa Clara City has a co-op of power company. It's a Silicon Valley Power, and their electricity is less than half the cost of PG&E. So it's PG&E is making a lot of money. That's what I'm trying to say. So they could. I think they in Santa Clara, the Silicon Valley Power, they have like a higher percentage of solar energy and all that kind of stuff. It's really great. It's a co-op. So I know PG&E is making a lot of money, but they're complaining about this, that during the day, okay, you can look down here, this sort of graph in gray, that's your solar power, okay? During the nighttime, right, 1, 2, 3, 4, 5, 6 a.m., you're not producing any power. Your panels are just on your roof, not producing any power. And then the sun comes up around 7, 8 o'clock, right? And you start to produce a little power as the first rays sort of start shining on that panel. And then it peaks, right around midday, noon, 1, 2 p.m. You get the most power out of your solar panels, and you get a lot of power going back on the grid because people don't quite need that much. And then right here around, 5, 6 p.m., of course, it depends on the season. This is an example. That power comes down as the sun sets, and you plateau off right at 0, right after sunset. So if you look at the energy, the total load on the system, okay, that's here in blue. This is a typical load. That's blue. So this is the gray is the solar energy. Blue is the energy consumption of typical energy consumption. So in the morning, right, you don't use that much electricity. And then as you wake up, right, throughout the day, you're using some more electricity. And then when people come back home from work, right, 5, 6 p.m., that's when you turn on your dishwasher, you crank up your stove, you're cooking the most in the evening, right? You're running your wash machine. The maximum energy consumption is actually during the evening hours, okay? Right, 5, 6, 7 p.m. And that's right when the sun is setting. So when you're going down to 0. So what happens is that if you combine sort of these together, if you look at the consumption in the blue and you sort of subtract off the solar energy, putting back to the grid, you get what they call a duck curve. Okay, that's this orange right here. And what it's saying is over here, right, during the daylight hours, the sort of the amount of energy that power companies have to produce, it sinks way down. They don't have to produce very much because solar energy is taking a lot of that load. But then right as the sun sets, they have to crank up all of their generators and deal with this peaking demand. You see this demand right here just sort of like skyrocket between like the amount of energy that they had and the amount of energy here that the power companies have to produce. So this is sort of, there's a lot of people working on this, a lot of research. And at UC Merced, there's someone, Dr. Quartz, she was from NREL. I think she's really cool. She gave a talk. I'm a fan. She's working on this. A lot of people working on this sort of problem on how to deal with this big spike in consumption because, for example, coal plants, nuclear, you can't just crank them on in an hour and go from 0 to full blasting power. Because, so for example, nuclear has to be pretty much stable day and night. It'll give you constant output. You can't ramp up and down a nuclear reactor very easily. It takes you can only do it over days, right? And same with coal. It's not very easy to ramp up and down. The easiest thing to sort of ramp up and down is actually natural gas. So it's sort of complementary to solar energy. You can get natural gas to sort of, if you all of a sudden demand is spiking, you can use natural gas to fill that demand. So yeah, that's one of the challenge of solar photovoltaic energy. So now I'm going to talk a little bit about solar thermal concentrators. So this kind of is a segue. Is solar concentrators, they don't have this problem as much because even though the sun sets, right, that energy, if it's really, really hot vessel that you've heated up with the sun, it's not going to go cold, in 30 minutes. If it's in an insulated container, you can use that energy for hours after the sun has set. And there are many ways that you can use that energy. You can use it to power a turbine or something like that. So we'll talk a little bit about that. So there are sort of two different types of solar thermal concentrators. So the first is an imaging concentrator, sort of. So let's talk a little bit about imaging optics. So you probably know if you have like a lens, you guys wear glasses, right? Some people wearing glasses. I wear glasses too. I'm wearing contacts. You just can't see. So if you have contacts, a lens, right? So you needed to create an image of whatever there is. So if you have an object here, so if you have rays coming from this point, okay, and they're going through the lens, all of the rays generated from this point on, say, a tree have to be focused on the opposite side of the lens to a single point, okay? And all the rays from, say, the bottom of the tree or wherever on the tree, they're focused over to the equivalent portion of that tree on the other sides. So as you can see, the rays do not intersect, okay? And in terms of solar energy, if you have something that's imaging, it has to track the sun because it's getting those direct solar rays. So an example of this would be a heliostat. Have anyone seen these? Heliostat? Okay, a few people. So I took a vacation to Zion last summer, and I actually saw one of these. I took a picture of it. Wasn't as good as this picture, of course. I took it from a distance, but there's like some like out by Las Vegas, in the desert, they have some of these. So these are made up of a bunch of mirrors, okay? And they're huge in area. And essentially those mirrors, like they track the sun and they're focusing all of the sun's energy. It may probably right here, up here. I think it's inside of here maybe. They focus all of the rays onto a single point and make it extremely hot, and that just like immediately, can vaporize liquid or whatever, and you can then turn a turbine and get electricity from that. Okay, so these are yes. Say it again.
During the day.
Yeah, during the day. Again, during the day. Yep. But you could also, heat something up if it was a fluid, you could store it somewhere and you could have heat later. Yeah. So when I worked on non-imaging optics when I was a graduate student. And so in non-imaging optics, you don't need an image. You just want to collect as much energy as you can. And you don't care that you get an image out. So for example, if you have rays generated from, say, this point, okay, they can reflect off of your concentrator and they can land at different spots, and you don't care because you don't necessarily need an image. You just want the maximum flux on that receiver over there. They don't have to be all the rays from this point don't have to concentrate to the same point over there. And they're non-tracking. That is the biggest advantage. You don't have to have any equipment that moves this around, because you can get, if the sun is over here, the rays come in and are concentrated, or if as the sun moves along the sky throughout the day, they're concentrated to different spots on your receiver. And so some examples of non-imaging optics, non-imaging thermal concentrators would be luminescent solar concentrators and non-imaging reflectors, such as the one in this slide. So again, you have some like source of the sun. This should be rotated 90 degrees, sorry, because the sun is usually from the sky. And then you have the aperture. That's where the rays come through the aperture, and then they're reflected onto this receiver. This is sort of the ideal theoretical concentrator design in 2D. And so you'll get like a trough, kind of like this. So the sun rays are coming down, they're reflecting off of this trough, and those rays are concentrated onto a metal pipe that usually has a fluid in it that's heated. It's usually oil, because it doesn't expand as much as some other liquids. So just a short plug for work that I did. So here's an example of a non-imaging concentrator, and I worked on segmented solar thermal concentrators. So we looked at, instead of bending it smoothly, maybe, you can save on manufacturing costs and by taking sort of a flat sheet and kinking it. And so you have like linear segments instead of like, having to manufacture it where you have to smoothly, very precisely bend the metal into a curve. And so I worked on optimizing sort of the vertices of where optimizing the shape for segmented solar thermal concentrators. So I'll give you a short video on that right here. Again, this should be rotated by 90 degrees. So here's the sun. And I'm just showing a few rays of like the hundreds of thousands that I sent through to imitate sort of rays from the sun being concentrated onto the receiver here. Can think of that in 3D as your pipe. And then we can optimize the shape of that concentrator. All right. And that's all I have for you guys. So now I'll open it up for questions. Yeah, Dana. Oh yeah, sorry. Oh, he's coming with the mic. Yeah.
Can you hear me? Yeah, we had solar put on, Jerry, when was it? 10, 12, 13 years ago?
13 years ago, uh-huh.
And I'm wondering if there's been a lot of progress made in how good they are at extracting energy. And I'm just wondering if ours are sadly out of date and need to be replaced. But anyway, we've had them for a long time, and it's great. Yeah, it's good. And of course, Palo Alto has a municipal utility district.
Oh, you do also. You don't have PG&E. You have
No,
something else. Okay,
no.
That's great. Yeah.
Yeah. So yeah, it's nice to think that we're getting this something sort of free, although it certainly wasn't free
when you bought
to
it.
install.
Yeah,
right?
yeah.
Although we got rebates and so on.
Yeah.
So I think it ended up costing around 17,000.
Yeah. Mm-hmm.
Yeah.
After rebates or before?
After
Rebates. Okay.
Yeah.
So I've been looking a lot into solar lately, so I can tell you because I've gotten quotes to put solar on my house. So your first question is, have they gotten better? Yes, they've gotten more efficient. Yes and no. So it depends on how much, which panels you buy. So in general, panels have gotten more efficient. Like the most efficient panels have increased in efficiency. So we've gotten, you can now buy more efficient panels than you could 14 years ago. But you can still buy less efficient panels for cheaper because, so the efficiency goes also with sort of the pure, I don't know too many of the details, but when they crystallize the silicon, you have to do it in a very controlled environment, and they slowly crystallize. And sort of from what I understand, the slower you crystallize it, sort of the purer you get the purity levels that you want. So, but you pay more for that, if the manufacturing process takes longer. So when I was looking at panels, I've been looking, for example, at REC panels. They're sort of they're quoted as some like luxury panels. They're like the highest, they're like one of the best premium panels is the word. So they have very high efficiencies, like 19 to 20% efficiency. So when you look at the efficiency, so you could have a lot of times when you buy them, you buy them by watts, like you buy a 400 watt panel, right? But if you're comparing between panels, you'd be like, oh, well, this one's a 400 watt panel. This is a 400 watt panel. That's the amount of electricity that they output. But one of them might be higher efficiency. And what that means is it's going to be a smaller panel, because what it's doing is it's a smaller panel. So it can get 400 watts out with the amount of sunlight that's on that smaller area. And you can get 400 watts out versus you could you could get a cheaper panel that's also 400 watts and it can output 400 watts of electricity, but it's going to be a larger area because it's not as efficient. So it needs sort of a bigger surface area, more cells to get 400 watts out. So the other thing is different panels, if you're looking, they have like an energy guarantee. So you've probably noticed that when you first installed your panels, you were getting more electricity than you are now, right? So they degrade over time, and different panels degrade at different rates. So if you, I'm leaning towards getting REC panels. That's what I got quotes on. So I think that's what I'm going to put on my roof. So maybe, I don't know if I'm not advertising for them, but they have like, they guarantee an only 0.25% degradation in energy output per year. And they guarantee that. And that's the lowest of any panel manufacturer that I've seen. And the other ones, what's standard is that they'll guarantee 0.5% degradation per year, which is double REC panels, but that's, still okay. But you can look at, I should have put a graph in, but you can, look at a graph online. So if you're getting so much energy output when they're initially installed, every year that energy output is going to decrease by about 0.5%. Well, over 25 years, which is about the length of time that you're going to have solar panels, that adds up. And they're only about 80% efficient at year like 25, as they were when you initially installed them. So you're going to get like 80% of the energy when you first installed them 25 years down the line. So 14 years and you're about, you're a little over halfway there. So you probably noticed them decrease by maybe, I don't know, it's about 10%, maybe less than when you showed us. Yeah.
Can you repeat her question because they
So her question, yeah, I don't know if that's a question. So she had some kind of computer program that showed how much electric output you were getting from your panels, but you haven't checked in with it for a while, at least. You don't know if it's working. Yeah.
I've got a couple people online with their hands up.
Yeah.
Michael?
I think Odette was before me. Raised hand.
Okay,
Yeah.
Oded? Yeah.
I have two comments. I work in both industries,
Uh-huh.
water heating and solar. Water heating, back in the early 80s, we built some concentrator for heating water. The material was glycol, which is the same stuff used in the radiator of the car. So you can get temperature higher than the boiling point.
Mhm.
And this was used for cooling of agricultural storage.
Mhm.
The concentrator was not a hyperbolic mirror, it was just Fresnel lenses. And you make the tracking by moving them left and right, up and down, but not any angular direction.
Mhm.
And this can give you, I was able to get like 6 millimeter exposed area of the collector, and the rest was insulated. And we can get very high efficiency. At 8:30 a.m., we can get boiling water. This was kind of thing. I don't know why they stopped doing it. Secondly, about solar panel, I was involved in aerospace. I think today you have much more advantage. First, reducing the resistance that REC is doing, dividing the panel to smaller 2 panels in parallel so you can get more current. Secondly, you have MPPT, which is peak power tracking, so you can get more power. Third element that we have recently is adding a mirror in the bottom of the panel, so the lights that don't have enough chance to create all the electrons is reflected back by a mirror, and the same material, same silicon, take it back again from the other side. And this increased the efficiency to more than 33%. So basically, a solar panel can do it. The main issue is we have to distinguish between industrial level of terawatt, watt, or gigawatt versus home. And I think home may be a good idea because now we don't need to have mega dollars of investment. So I think home is good idea. The only issue with that is storage of the energy. And I think with today smart electronics, you can run your washing machine and everything that you need at the time of peak power from the sun. So about cooling of the house in the summer, which is like to California, you can cool the house in the mid of the day. So when you come back home from work, the house is cool. So you don't have to start your air conditioner when you come back home. You can start it earlier. Batteries, I think we're going a lot of advancement in batteries today. And today you can get called the lithium iron phosphate, which is have many, many years of service. So I don't know why the government don't recommend getting what's called
Sorry, what was was that a question? You don't know why the government doesn't recommend what?
getting subsidy for batteries.
Oh, batteries. Oh, there is a subsidy for batteries. You can get with the Inflation Reduction Act, you can get 30% tax credit, like tax break on your solar batteries as well.
I think
Like for battery backup. It's panels and batteries.
I think
Yeah.
We've got three people with their hands up.
Yeah, but so just to briefly answer your first question, so why the I think you said it was glycol was used in solar, some solar thermal concentrator that you had, and it's in radiators and cars. Well, it could be that maybe that's not an environmentally friendly substance, and if there is a leak or disposal of that, like I know radiators in cars, right, the AC and stuff has changed throughout the years. So that's maybe a sort of a downside of solar thermal is that whatever substance you sort of heat up, if it does leak, it can be a big mess problem. Yeah. So yeah, but what everything else you said is excellent. Yeah, it's increased a lot, and there are tax credits from the government, and solar has advanced in batteries and solar over the years. Yeah.
The main problem is I see today is most of our industry is service rather than manufacturing. In the old days, manufacturing was done during daytime when you need lots of energy. Today, we don't do manufacturing anymore. And the result is the daytime energy requirement is very small. And most of the energy.
Daytime energy requirement is small. Okay. Yeah, but like you said, it's all in what you previously mentioned is they have like if you buy like a washing machine, I was looking at washing machines or dishwasher, everything's becoming like a smart dishwasher, so you can run it during the day. Washing machine's a little more tricky because like you can wash it during the day, but then if you're not home, who puts it in the dryer? Maybe we'll have like more dryer washer combos that maybe it'll wash and dry during the day when you're not home and you come home. Yeah, but yeah, we're moving there. Yeah.
We go on to Michael.
Yeah, let's go next question.
Yeah, thank you. Christine, I was delighted by your presentation because my master's degree was in optics and semiconductors. So I'm familiar with this branch of physics. One, my question is rather technical. So when you modeled to find this optimal shape of this optical curvature, so my impression that you use sort of numerical simulations approach for this.
Yes.
And I'm wondering if this could be done analytically, maybe. And my second question is that about the best roles of photovoltaics and thermal thermal energy.
About the what? Can you say that again? About the what of photovoltaics?
The best role of these two ways of using solar energy, photovoltaics and thermal.
That's role of photovoltaic.
Best role of photovoltaics?
Yeah.
What do you mean by best role? Best role in?
In using them, because my impression is that small scale, like what you put on your roof,
Yes.
is mostly photovoltaics.
Yes, yes.
And thermal energy is used for large scale.
Yeah, it's more commercial. Yeah.
But if people use this battery storage in their houses, would it change it? Because it could smooth this curve of
exactly. Yeah. So I'm not on the manufacturing side, but I would like to see more of the solar thermal at the residential scale because you know, I mean, I bought a house and it has forced air, but you know, you can heat your home with like hot water, you know, going through the floor. So you can easily have like solar thermal heating. And so I would like to see this more residential. It's a very cost-effective way of doing it. It's more efficient to put solar thermal on your roof to heat your house than to put a ton of solar panels on your roof and then you have, you know, electric conversion losses, and then you have to, you know, heat up some element and heat up the water, and then, right. So it, yeah, I would like to see sort of a combo of both in the future on residential. And so that's, I mean, that's, yeah, the best role, I mean, solar thermal is best for heating and solar photovoltaics are best for producing electricity. So if you want to run your dishwasher or your washing machine, you want to run it on photovoltaics. But if you want to heat your house, then, or your water heater, then it's solar thermal is better. Yeah.
Okay, Randy.
Oh, thank you.
Mm-hmm. But yeah, good question and good.
Hi, well, thank you.
Mm-hmm.
I'm interested in the thermal as opposed to the electric,
Yeah.
you know.
Mm-hmm.
Back in, give you a little history, I'll try not to be as lengthy.
Mm-hmm. It's okay.
Back in 70s, when I was really into solar age
Yeah.
and building a house. Oh, thank you. And building a house, I dismissed at the time solar
Yeah.
on the roof,
Mhm.
water systems,
Mhm.
etc.
Mhm.
And eventually what I did, I created a passive solar system. Now I had to consider the latitude and the angle of the roof
Yep.
for the peak in the
Yes.
winter.
Mm-hmm.
This was in Vermont.
Mm-hmm.
And so the solars created a solar sun space,
Mm-hmm.
a concrete floor in that space,
Uh-huh.
rock storage, and circulating fans that when the sun wasn't out heating the whole house anyway,
Mm-hmm.
could take that heat out of the rock storage. So that's, I'd like a little more talking about that if you have comments or thoughts about it. And the other thing is the life cycle cost of especially the photovoltaics.
Mm-hmm.
Now, you know, my solution was for heat,
Yes.
not for electric.
Yep.
Thank you.
Yeah. So that's great that you did put in some solar thermal and you sort of retrofitted it, as you said, when you built it, you weren't thinking about it. But yeah, of course, the direction your roof faces is important. I wish there was more regulation about that. So for example, in Germany, if you build a new house, your roof line has to face in the direction so that you can easily put solar panels on it and get sort of maximum efficiency out of those panels. And I think that would be good because it makes it then later, if someone doesn't put on it, maybe you build a house, but you don't put solar on it, if someone else buys your house, you can put it on it and you get really high energy output, like, because you get obviously the most energy output if it's facing south. So if you're building a house, it's definitely something to consider. Two, I think you mentioned sort of life span. So payback cost. So photovoltaics they pay back themselves really fast in California because we have some of the highest energy costs for electricity in the United States. We have PG&E is very, very expensive. And so you can pay back your upfront costs in 3 to 5 years. And then if you think about that, then from year 5 onward is free electricity, and you are just putting that all in your pocket up until year 25. So even if, yes, solar panels degrade, as we mentioned from Dana, you get less energy output at year 25, but only about 80% a lot of times, unless you buy the premium panels, and then you might get like 90% output of when you initially installed them. But even that 80% you get, and I mean, it's not like they just degrade and they decrease in efficiency. Like at year 30, maybe you're at 75% efficiency, it just keeps going down, but that's still free energy. Unless the only advantage would be if you needed that rooftop space, you could switch them out with more efficient panels and get more electricity if you needed that. But, I mean, at some point they do degrade to the point where you would want to like switch them out. But I would say in terms of cost effective, it's definitely very cost effective, especially in California, especially here, because our electricity costs are so high. But yeah, solar thermal too, I would say is, they're both cost effective. Yeah.
Okay, Zen.
Thank you.
Mhm.
Actually, my voice is coming out, out fine with the mask. So
Yeah.
I have two very simple questions. So
Yes.
as far as I understand,
Mhm.
you grow silicon by starting with like a little ingot, and then you gradually make the silicon lattice, right? You kind of pull it out, and so you make this 3-dimensional
Mhm.
lattice.
Mhm.
How does that work if you only have 4 valence electrons? That's my first question.
Oh, mhm.
My second question is, what do you think, or what did you think of
Yeah.
Cylindra as a technology?
Cylindra.
Yeah.
Oh, you have to expand on that. The first one, I'm not too familiar with how silicon wafers are grown, actually. I Googled that last night and I looked at, I was reading different things. So there's different processes to manufacture. So I'm not exactly how they grow these, the silicon crystalline lattice, but from what I was reading is that as the crystalline lattice is formed, when you dope it, they'll introduce sort of like a boron gas or something, and that produces those minute impurities to get your doped layers, so the 4 valence electrons, so that's exactly what produces a tetrahedral. Like, I can, if we have internet, I could also pull up a different picture. Oh, this is not shared. Let me share. So this is the 4 valence electrons. That's exactly what makes that tetrahedral structure. You have sort of a center atom, the center atom, and then atoms on each of the 4 corners of a tetrahedron. That's why it's like the tetrahedral shape. So this is a 2D representation. It doesn't look like, it's not the tetrahedral shape, but this is sort of like a representation to get the point across of how they're connecting. So each silicon has 4 valence electrons, and then this is one silicon, here's another silicon, and this silicon has 4 valent electrons, and these 2 electrons form a bond, a covalent bond. So that's how they're.
You only have 4 electrons.
Yes.
You can only build a 2-dimensional structure.
No, it's a tetrahedral structure. Here, let me. Is there internet here?
While she's searching, I want to make a comment. When you get the microphone, remember, point it at your face in this direction. Don't talk like this. It doesn't get loud enough. Okay, please?
So it looks like this. So you have a silicon atom here, and this is another silicon atom, and then you can think of this as a lattice. So this silicon atom is connected here, but it's also connected over here, here, here. Like, let me see if I can get the whole lattice. It's like this, okay? Oops, let me scroll down. So, of course, this is not quite all silicon. This is some other stuff too, oops. But you'll get like, it's connected in a lattice. This is a silicon and oxygen, it looks like, but I don't know, I'm not finding the exact.
Thank you.
Yeah. Does that make sense?
Yeah.
Okay, great. Yeah, so no, it's definitely not 2D. It's a 3D
Right.
tetrahedral structure, and it's crystallized. And I don't, you can read about it. I'm not an expert on that, but I was just reading, yeah, that they inject some like boron gas, and that a minute amount of boron will, kind of then be injected into the crystalline lattice as it forms. Mhm.
Okay, Matt, you've had your hand up for a while.
Oh, yeah. Oh, so can you, what is Cylindra actually?
It was a company that was actually subsidized during the Obama administration. They were located up here in Fremont along the 880.
Okay.
And they made a solar panel that kind of had like a little cylinders that would capture the sun, I guess, at different angles. It kind of resembles your parabolic heat grabbers, or
Was probably trying to increase efficiency by
Right.
getting more sunlight. So, my opinion is, yeah, you can do that, but the manufacturing process is going to be obviously more intensive because now you have these 3D structures. And so, is it worth the little bit added efficiency? I mean, a lot of times. So even they recommend, in terms of efficiency, if you have a huge area and you don't care about space, they'll recommend a little bit lower efficiency panels because they're cheaper. You can just put a ton of panels on there and you'll get all the electricity that you need and save some money. If you're residential, for me, I have only a small south-facing rooftop that I can use that get maximum. So I'm going to put the most efficient panels on there to get the most electricity out of my house. Yeah, so it depends on your usage, but
I mean, I know that the Cylindra panels were not the most cost-effective approach, and I think that's what killed it, because they say you could buy a panel from China, which was not as efficient, but you recouped it through the
a lot
cost.
cheaper.
But I was asking, but just strictly the technical question: how much, how many more amps would you get out of a Cylindra panel versus an equivalent, other photovoltaic technology?
I'm not sure. I'd have to look specifically at Cylindra. I could Google that, but I'm not sure. Yeah, I mean, yeah, I don't know actually. And if there's some 3D shapes, I also wonder about shading. So that's another thing. So with solar thermals, you or like sometimes if you've seen parking, anyway, if you have solar panels at a tilt, like above carports or something, you want to make sure they're not shading the next like chunk of panels over. So I had to look specifically, but I'm not sure. Yeah, how much
Okay,
more efficient.
Matt, you're up.
Yeah.
I have some
Okay.
comments, if you don't mind. The labor to put a panel is
what's going on?
about $1,000 per 5
Yeah,
kilowatt.
Oded, could you wait for Matt?
Oh, I'm gonna mute him real quick. Sorry,
Okay.
I muted you, Oded. We'll come back. So I promise. Okay.
All right, just real quick. Christine, you said that the net metering was ending or possibly ending.
Possibly, yes.
Do you know what would replace it, if anything?
Yeah, it's terrible. I mean, terrible for you as a consumer. So from what I read the draft or some of the main points in the draft. And so what it said is, so right now you can connect your solar panels to the grid like for free. You like whatever you're paying in PG&E, you can connect your panels to the grid. You have net metering, you like give electricity back. And your meter runs forward and backwards, as I mentioned. And then also in an over 1 year span, if you've sold more electricity back to PG&E than you got, you actually get a check. You get money from them. It's a small amount. They pay you pennies, but that's okay. Like you get a small amount, way less than what they charge you. I think they charge you like 39 cents per watt or something. Or I don't remember. It's really high. So they give you like 2 cents. If they charge you 39 cents for electricity, if you sold to them, they give you like 2 cents in excess. But it's a small paycheck, but it's a good deal. You get overall, the net metering is the main part. So the new one would be that you would have to pay a fee every month to be connected to the grid to sell your electricity back. I think it was like $15 or $20, like base. That's like a base cost just to be connected. And then the second is that net metering would go away, and they would essentially what happened is that during the daylight hours when they're taking your electricity, they would take it and give you very, very little for it, which is kind of what they do if you have an excess. But then at the nighttime, they would charge you regular price, from what I understand, for your electricity, which is that 39 cents a watt. So what would happen, because you probably know if on your bill you have like time of use. So during the daytime, your electricity is cheaper anyway. And then from 4 to 9 p.m., PG&E hikes up the rates and it's more expensive. So what would happen is they would say, okay, you can sell us your electricity in daytime hours. We're going to give you a really, really tiny price for it. But then at nighttime, we're going to charge you premium top dollar for any electricity that you take. So it's essentially forcing you to get batteries if you want, because they're trying to get people to get batteries to take their own energy from the evening, which is going to increase the cost for you a lot to put on solar on your rooftop. And it's going to increase the amount of time before it pays itself back. And then it's going to increase the cost every month because you have that base cost of like 15 or I can't remember how much, $15, $20 just to have solar and to have the option to sell it back to PG&E. They're like, we don't want it. Store it in batteries, use it yourself. We don't want to take your energy and sort of, because it is a hassle for them. They have to distribute it. It's like they're getting this solar and they're like, oh, now we have to distribute it. And as I showed with the duck curve, they have to deal with this distribution sort of that they're getting a bunch of energy during the day, more than they need maybe. And then at the nighttime, they're like, whoa, we have to ramp up every generator and during that peak demand right around like 5, 6, 7 p.m. Yeah. So I understand that it is a problem. We need to get people to switch over to sort of smooth that duck curve is what they're trying to call it, smooth. So you don't get that huge spike in energy production that you have to have in the evening hours. But as a consumer, you should get solar right now if you can get it. Yeah, that's what I've read. Mm-hmm.
So real quick, is it basically wholesale pricing is what you're going to get?
Right now you're getting like wholesale pricing. It's like if you give them a kilowatt of energy during the day and then you take a kilowatt of energy at night, you're flat even. You pay nothing. Like if you give during the day and you take at night the same amount, you don't have to pay anything. That's net metering. That's a great deal. You should try to get it. It was implemented to increase to speed up the payback time of your solar panels. And that's what makes you payback like 3 to 5 years. So if you this is also another caveat. If anyone knows someone that's a contractor, so my dad happens to be a retired building contractor. So I know you quoted some costs were really expensive. So the installation is about half of the cost. So I was looking and I can put a system on my house and then I had other people with installers give me a quote too. So it's like $12,000 if I buy the panels, inverters, everything. My dad installs it for free because it's my dad. I'll help him out. And he can enjoy some California sun because he's in Minnesota. I'm from Minnesota originally. So he's going to stay with me some months and be maybe a snowbird and enjoy my solar electricity in the winter months. And then, but if I were to pay someone to install that, it would be before incentives, it would be like $20,000 to install the same system. So if you, I'm just saying, if you're a do it yourself kind of person, you can cut the cost of your solar in half, and then your payback time is going to be only a few years to getting that back. And then this is before the incentive, so you can, whatever you pay, 30% of that you get back in a tax credit. So if you paid $10,000 for solar, you'd get $3,000 back in tax credit. Yeah,
we have a question on the chat room. You want to read that, Scott?
Yeah.
Or you can call on the person who wrote it.
Oh, who wrote it? Stuart.
oh yeah, I can read it here as well maybe. Stuart, thank you very much for your presentation. Numerically, what is the advantage gain? Whoops, sorry. This just popped up. There it is. Numerically, what is the advantage gain of solar energy capture per square area comparing typical PV panels versus the solar concentrators in the reflector and concentrator rods or tubes? So what is the gain of energy capture per square area compared to PV panels? So you're sort of comparing like apples to oranges a little bit, because as I mentioned, I think you're talking about energy gain. So if you take the typical PV and you, which is like the highest quality panels are about 20% efficient. Okay, so you're getting like 20% of, you know, what it's converting 20% of the sun's energy into electricity, and then you have some losses with your inverter and things like that from converting the direct current to AC alternating current. And then, of course, you get different, and then you're going to heat up. Let's say you're using it to heat up your water heater. You have electric water heater. So you have losses in, you know, that your water heater is only so efficient and converting electricity to hot water. So that's a lot of losses. So if you're looking at using photovoltaics, for example, hot water heating, it's not very good. You're much better off using solar thermal to heat that water. In terms of running your dishwasher, well, then residential scale solar thermal, you just can't really get that. I mean, it's too many moving parts. So if you want to convert solar thermal to electricity, most of the time you need like that heliostat, and you need something like you get extremely high temperature where it's like water is immediately vaporized, and that is used to power a turbine, and that turbine then creates electricity. So you have like lots of pieces of that, right? You have like all those mirrors, concentrated single point. Then you have some, you know, vaporizing. You have wind turbines, and that motion of the wind turbines then being created into electric current. So if you want electricity, go with photovoltaic, especially for solar, and probably for like most small scale commercial, unless you're super huge. If you want heat, go solar thermal. One to the other is not, you're going to have it's just not as equipped to do. You're going to get more losses going from one to the other. Does that make sense?
Yeah, Jerry, you had a.
Yeah, I just wanted to mention a different kind of solar process.
Mhm.
My dad read an article in the late 40s or early 50s by an MIT professor about uses of solar. And so on the south wall, he installed a homemade system with sunlight goes through 2 layers of glass. It's aluminum painted black, heats up an airspace that's about 8 inches wide.
Mhm.
And then there's a fan that blows it through the house.
Yeah.
It's very simple. It only
Yeah.
cost a few thousand. That was a long time ago, but it only cost a few thousand.
Yep.
The maintenance on this was simply a few drops of oil in the fan once a year
Mhm.
and painting the wall, I don't know, every 10 or 15 years or something.
Mhm.
And it cut our cost of heating in half.
Oh yeah.
We had a big gas furnace as well. This
Mhm.
is in Massachusetts, you know,
Mhm,
it does
mhm.
get pretty cold. So
Mhm.
that's all.
Yeah. No, I agree. Like you have to have your house built the right way. So even in my house, I have this huge in our master bedroom, we have this huge double like sliding glass door, and I'll open the curtain in the morning, even like I did in November, and it heats up the room because the sun, it's east facing, sun comes through there. It heats. It's pretty amazing. That room will be warm, and they go in the rest of the house is cold. But yeah, it's essentially the setup. Yeah, you have to have the house built south facing. You have to have that big area, glass area south. No, great. That's excellent. No, I wish more houses were designed. We need to design houses with solar in mind, like passive solar like this, more passive solar, just sun coming in the window. Yes, excellent.
Okay, this should be the last question. Now, Oded, you could
Oh, yes.
be quick. Yes, make it short, please.
Oded. Yes.
You're still muted.
Yeah, sorry. You can unmute yourself, Oded.
Okay.
Yep.
About this $20 for using the network, the distribution of PMG or cover, it's been there for 5 years. I have my panel for 5 years, and every month I pay $20 for the right to use electricity during the time when the solar panel is not running, just for the right. So this $20 is not new one, it's old one. What
Okay.
nasty is when the peak hour was starting at 2 o'clock in the afternoon, when factories and office need lots of air conditioning. Now they move the peak hour from the industry to the residential. And therefore, now they charge me to subsidize the industry. That means when I, in my office, and the solar panel create power, you say, no, we charge the office high price and you get low price because not peak hours for your home. So what they done is separate home and industry to their advantage.
Yeah, they're always going to do to
The
their
government
advantage.
don't say anything about that.
Yeah, of course. Yeah.
Secondly,
So,
okay. You mentioned about what kind of panel to buy. I am an engineer, so I know what I'm doing.
Mhm.
And the cost of the panel itself is about $1 per watt. The cost of the inverter and the hardware and the distribution is another. So it comes
Yes.
altogether like $7 per watt. The
No,
charge-
okay, yeah, if you install yourself, it's $2 a watt. So I just got a quote, I can get it for $1.93 or $1.92 per watt. It's inverter plus panels, if you install it yourself, yeah.
Yeah, if you do it yourself.
Yeah,
Now
it's
today-
probably double that if you, like, yeah, $4 a watt if you install it with someone
So
else.
if I want, my point is, if I want 5 kilowatt hour, 5
Mhm.
kilowatt system, which is normal house,
Mhm.
I will pay if I go to contractor about 20,000. If the material that you have to buy is about 7,000. So the rest is profit and labor.
So it should be around 20,000 with labor. I got a quote for a 6K
Yes, the
system
rest-
for 21,000 with installation costs.
Yeah, this I say profit and labor is 21. Material is 7. The rest is labor and profit.
Yeah, material is like 7 or 8, and then and then labor and profit is the rest. Yeah. Yep,
So
that's right.
basically, the level of profit is almost 3 times.
Yes.
And
Yeah.
I say, okay, so because of this high level of profit, for me, it's buying the best of the panel would be the most effective cost per kilowatt hour.
Because you're putting more money into your panels instead,
Yeah.
because installation cost is expensive. Yeah. So if you have more panels and they're lower quality, then you pay more in installation costs and you don't get the electricity out. Yeah.
But nobody teach us about that.
Yeah. I mean, it depends on, again, if you're installing them yourself or,
But people
yeah.
need the.
and if you're residential, if you're commercial, then, maybe you can strike a deal with the installer. And if it's very standard, it depends. I would say go for the higher efficiency panel, but
I know
yeah.
that.